up, guys? I hope you understood Riemann integration. We discuss this definition here. We are mainly talking about the continuous functions on closed interval, right? So so we know that there x is a number that satisfies this inequality. So lower sum is smaller than that number and upper sum is bigger than that number, right? For each particle, that number is called the integral of f over AB interval, which is denoted by this. So I think you remember we have completed this first problem. So if the function is a constant one over this interval, closed interval, we showed that the integral of f over this interval is this one. So now I'm going to discuss the second one, the function. So here we don't. So this function is not a constant function, which is is equal to x over this interval. So let's try to show the integral of f over AB interval is given by this. Let me take the blackboard. Alright, this time the function is defined. X so consider AB interval. Alright. Okay. Now let's consider any partition, right? So let P be a partition of AB interval. Let P be a partition of AB interval, right? And the lower and upper sums. So upper sum of f corresponding to P partition is given by this summation. It goes from 1 to n, capital M sub I, xi minus xi minus 1. The width of this subinterval, right? So here look at this function here. That function is increasing, right? So suppose this is subinterval xi minus 1. This point is xi. So the function value at this point is f of x sub I is 1, f of x sub I minus 1, right? So this function is increasing, right? So if you consider the midpoint of this subinterval, what is the midpoint? Blow out that picture here. So let's blow out this subinterval. This is your x sub I minus 1. is x sub I. You consider the midpoint x I plus x sub I plus x sub I minus 1 divided by 2. So this is the midpoint of this subinterval, right? So because this function is increasing, so the function value of the function just a second, right? So this is the midpoint. The corresponding function value is this one. So for this point, this is the corresponding function value. This is f of x xi. So I think you know that, right? No, wait a minute. So this is the function value at this point is f of x sub I minus 1. The function value of f at this midpoint is f of xi plus xi minus 1 divided by 2. Right? Since this function is increasing, right? So this is the maximum of f over this on this interval, and this is the minimum of f. So basically this is your capital M sub I. This is your simple M sub I. So the midpoint, the function value at midpoint is here. It is this one. You know the function f of x is equal to x. So this one is same with x sub I minus 1, right? This one is x sub I minus 1, and this one here x sub I. Then simple M sub I is equal to x sub I minus 1. Capital M sub I is equal to x sub I. Alright, so so then the upper sum this is x sub I times xi minus x I minus 1. This is the upper sum. Similarly, you can find the lower sum. What is the definition of lower sum? Lower sum of f corresponding coefficient p. So here, note that this partition. So this partition here can be any partition of a and b, right? That's why it is very important, right? I goes from 1 to n. Simple mi m sub I x sub I minus 1. That is our simple m sub I, which is x sub I minus 1. This one is x sub I minus 1, xi minus xi minus 1. So we know that lowest sum is of f corresponding to partition P is less than that is trivial. Wait a second. Right? So we know that xi, so this is our xi, and this is our right hand side then. X, this is left end of that interval. This is right end, right, and this one is the midpoint, right, plus x sub I minus 1 divided by 2. We know this one here. So here we are focusing on xi minus 1, x sub I sub into, right? So the average of these 2 points is the midpoint of the subinterval. So this is true, right? I multiply whole equation by the width of the subinterval. X sub I minus 1. What is the width? xi minus xi minus 1, which is a positive value. xi plus xi minus 1 divided by 2 multiply by the width of that interval. Wait a second. So I multiply whole inequality by the width of this subinterval, then we get this inequality here. This is true for all I goes from 1 to n, right? I take the sum. I goes from 1 to n, sum. So what is this one here? Sum of x sub I minus 1 times the width of this subinterval, which is the definition of, lower sum of f corresponding to b, lower sum of f. So this is same with lower sum of f corresponding to b, partition p, and this is exactly same with the upper sum of f corresponding to p, partition p. Right. Let's write this down properly. Lower sum of f corresponding to partition p is, so 1/2 is, you can pull out from the summation mark, and sum here x, here we have xi plus xi minus 1 times xi minus xi. minus 1, which is xi square minus xi minus 1 square less than or equal upper sum of f. So right, so the first one, when this summation goes from 1 to n. So the first term, just sub this one into here. So x sub 1 squared minus x sub 0, which is x sub 0. Think you remember x sub 0 is equal to a, x sub n is equal to b. Then if you simplify this summation, you get b squared minus a squared. So lower sum of f is less than or equal to 1/2 b squared minus a squared, and this number is less than or equal to upper sum of f. For each partition, for each partition P of AB interval, right? AB interval. Therefore, this number should be equal to this number. Using the definition, this number should be equal to integral of f over AB. So this is the proof of the second problem. Now you can try the third problem here. So try this one on your own.